So, hello everybody. My name is Tatjana von Landesberger. In the name of my co-chairs, Michael Gleicher and Ivan Viola, I would like to welcome you to the Eurovis paper session. This session features the best papers at the Eurovis full papers track, and we have one best paper and 3 honorable mention papers that have been selected out of 168 papers. And the process of choosing the best paper awards was by using the first 168 papers that were submitted. And out of them, we accepted 48 papers with an acceptance rate of 28%. From the accepted papers, committee selected 1 paper and 3 honorable mentions from an initial selection of 10 papers based on their top scores. And we would like to very much thank the Best Paper Committee that consisted of Heike Leite from TU Kaiserslautern in Germany, Jeffrey Hare from University of Washington, USA, and Yunhai Wang from Shandong University in China. Based on their recommendation, I would like to congratulate to the best full paper at the Eurovis, which is presented to the paper called PICS, Interactive Visual Pattern Search in Sequential Data Using Unsupervised Deep Representation Learning, which is co-authors by Fritz Leschkas, Brad Peterson, Daniel Hehn, Eric Ma, Niels Gellenborg, and Hans-Peter Pfister. So big congratulations to the awardees. And according to the committee, this paper contributes a clear improvement to the state of the art for visual pattern search, leveraging interactive machine learning methods. The work covers multiple tasks and use cases, provides a compelling evaluation, and the resulting tool is available to the community as an open source software. So congratulations very much to the awardees, and I'm looking forward to the presentation. Before we start with the presentation of the best full paper, I would like to congratulate also to the honorable mention papers, which is phase space projection of dynamical systems by Nemanja Bartolovic, Markus Gross, and Tobias Günther, as well as to the second honorable mention paper called Infomages, Embedding Data to Thematic Images by Darius Coelho and Klaus Müller, and Localis, Locally Adaptive Line Simplification for GPU-based Geographic Vector Data Visualization, authored by Ali Reza Amiradam, Daniel Adil, and Renato Paorola. So big applause to all the 4 papers. These 4 papers are presented both at the regular sessions and also today in the best paper sessions. So the attendees and the presenters have more possibilities to communicate with each other. So if you have questions to the paper, please use the YouTube channel or the Discord channel, and I will collect the questions during the session and then post them after each talk. Please use your name and tag questions within queue. And now, big congratulations to all the awardees. And now we can start with the paper presentations, starting with the first paper, PICS, Interactive Visual Pattern Search in Sequential Data Using Unsupervised Deep Representation Learning. Thank you very much, and congratulations.
Hi everyone, I'm Fritz, a PhD candidate in Hans-Peter Pfister's Visual Computing Group at Harvard University, where I'm working at the intersection of data visualization and computational biology. to enhance multi-scale visual pattern exploration in genomics. Today I'm going to present peaks, a tool for interactive visual pattern search in sequential data that uses unsupervised deep representation learning for similarity comparison. Visually searching for patterns in sequential data can be challenging when the search space is large, the patterns are complex, or the query is difficult to formalize. To overcome these challenges, we need an effective feature representation that captures important visual properties for similarity comparison. Such features could, for example, be the number, height, or position of peaks, the maximum, minimum, or average value, or the noise level. The feature representation of the data is typically defined up front. While this is useful for finding specific patterns, it requires a deep understanding of the data and often does not generalize well. For instance, in this example from biology, analysts often want to determine the number of peaks, as those act as proxies for biological events. But without domain expertise, it's hard to tell whether we should count 5 or 7 peaks in this example. Also, what if we want to capture peaks of other shapes? To improve upon existing pattern matching techniques and provide a generic solution, we have developed a convolutional autoencoder model for unsupervised feature learning. Given a region of sequential data, the first part of our autoencoder model learns a latent representation that the second part of the model uses to reconstruct the input data. By having a lower dimensional latent representation, the autoencoder is forced to learn an abstraction that captures the important visual features of the data. Additionally, to support interactive visual pattern search, we not only need a good matching technique, but also a system that is able to adapt to the user's perceived similarity. We have developed a system called Peaks that uses our novel representation learning technique and combines it with an active learning strategy to allow users to interactively train a classifier that identifies the important visual features using binary relevance feedback. Now, the first question we have to answer is whether our proposed representation learning technique is able to capture these important visual details of the data. Here we can see the reconstruction results for a genomic assay called DNA sequencing. Each column shows 3 examples of a particular size, but ultimately each region is aggregated into a vector of size 120 before being encoded with our convolutional autoencoder. For each example, the original data is shown in white, the reconstruction is shown in blue, and the difference between the two is shown in the pink-blue chart. Overall, we can see that the autoencoder provides a smooth reconstruction of the input data and is able to encode most of the salient visual features. We also see that as the size and pattern frequency increase, the reconstruction loss increases as well. Numerically, we see the same picture. The R-square scores, which tell us how much variability is explained by the reconstruction, decreases from 0.98 for the smallest region to 0.78 for the largest region. But reconstruction wasn't our actual goal, so you might ask, is the learned representation also useful for similarity search? And the answer is yes. We compared our technique to a set of 6 other commonly used techniques for similarity search in sequential data. To do so, we defined a set of 9 diverse search patterns, which are shown here in the top row. For each of these search patterns, we extracted the 5 most similar regions found with our technique: Euclidean distance, symbolic aggregation approximation, dynamic time warping, normalized cross-correlation, UMAP, and a tool called TS-Fresh. Looking at some of the details, we see that each of the other techniques can fail to capture important aspects of the target pattern, as highlighted here with these pink boxes. And while no technique provides perfect results, our autoencoder model is able to consistently capture more important visual aspects. And we were able to confirm these anecdotal results in 2 user studies on Amazon Mechanical Turk, where we found that the 5 search results from our technique are perceived significantly more similar to the target pattern than the results of any other technique. But so far, we've used all features or dimensions of the learned representation equally for similarity comparison. However, the notion of similarity can vary by person and search query. For instance, sometimes only the number and shape might be important, while other features like the position and magnitude might be irrelevant. To provide a generic approach for visual pattern search, we built peaks around an interactively trained binary classifier that operates in the learned feature space and tries to identify the features that are important to the analyst for a given query. The training data for the classifier is provided interactively by the analyst in form of binary relevance feedback. And so ultimately the goal is to train a classifier that finds regions in the sequential data that are perceived similar to the search query. Since many datasets are large, we additionally need a sampling strategy that focuses the interactive labeling process on a subset of regions that are useful for training this classifier. In this regard, we developed a sampling approach to select regions which the classifier sees as uncertain, which are located in dense neighborhoods, and are relatively close to the search target. The intuition behind this sampling strategy is the following. Labeling uncertain regions in dense neighborhoods is likely to improve the learning effect and thus make the labeling process more efficient. The initial focus on regions that are relatively close to the search target will ensure some level of similarity between the samples and the search target, which can help to concentrate the labeling process on meaningful pattern differences and also keep the analyst happy or satisfied during the labeling process. Now let's take a look at the user interface to see how all these aspects play together. The interface of peaks consists of four main components. At the top is the query view, which shows the region defining our search query. The view is pan and zoomable to allow free exploration of the entire dataset. Below the query view is a list view which represents different regions of the data for comparison and labeling. And depending on the tab, the shown regions here are either selected by our active learning sampling strategy for exploration, or they're defined by the results of the trained classifier for exploitation. For debugging, it's also possible to look at previously labeled or manually selected regions. Importantly, every region here features three buttons for labeling them as either matching the search query, not matching the search query, or being inconclusive. At the top of the right sidebar is the embedding view, which shows a 2D embedding to explore regions based on their latent representation coming from our autoencoder model. In this view, every region is represented as a dot and color encoded to its label, where blue indicates a positive match and pink indicates a negative match. A secondary light gray to blue color map encodes the dots by the classifier's prediction probability, where dark blue indicates that the classifier is certain that this region matches the search pattern. And finally, at the bottom right is the progress view, which visualizes the classifier's uncertainty, the overall change in the prediction probabilities, and the convergence or divergence of prediction probabilities for every training to help users determine when to stop the labeling process. Here the inner and more saturated bar is relative to the set of already labeled regions, and the outer bar is relative to all regions of the data. Now in the following I'll show you a brief example of how peaks can be used to build a classifier from scratch. In this example we're looking for pairs of overlapping but slightly shifted peak-like patterns. In order to build a classifier for our search query, we need to provide feedback to the system in form of binary labels. We start labeling regions selected by our active learning sampling strategy as either matching our search target, not matching our search target, or being inconclusive with clicks on the corresponding button. At the end of the initial sample set, we'll train our first classifier and then receive a new set of samples. And as we continue labeling regions and training classifiers, the progress will keep us informed about the state of the learned classifier. For example, we can see that the uncertainty is gradually decreasing. Now to gain an overview of all regions, we take a look at the embedding view. Using the prediction probability color map, we can identify neighborhoods of regions that contain potential matches. We could use the embedding view to explore these regions in detail using the lasso tool, but for now let's turn our attention to the results to assess the current performance of our trained classifier. Besides just browsing the results, we can further improve our classifier by continuing to label regions to confirm true positive predictions and to inform the classifier about false predictions. After several rounds of labeling and training, our labels can disagree with the classifier's predictions due to inconsistency. Peaks notifies us about such conflicts to encourage resolving these issues. For instance, here we fix some incorrectly assigned positive labels, which we do not consider matches anymore. Once we're happy with the current results, we can explore the entire dataset in the query review. To guide this exploration, the query review visualizes the prediction probability as a light gray to dark blue heat map, where again dark blue represents strong matches. This way we can quickly find other regions in the sequential data that exhibit similar patterns to our search query. We evaluated the usability and usefulness of peaks in an in-person user study with 8 computational biologists on a simulated dataset, and first of all found that peaks is easy to learn and use. A 15-minute introduction was sufficient to enable the participants to successfully build and refine pattern classifiers. But more importantly, we also found that on average, the classifier's performance was higher when trained on the experts labels compared to training the classifier on the ground truth labels of regions sampled with our active learning sampling strategy, which indicates that the expert-steered training can be more effective than an automatic approach. To conclude, we showed that modern machine learning techniques can be used to improve interactive, user-driven exploration, and we hope that others will use peaks with their own data and maybe even extend it with new encoder models. For more details, please refer to our paper, and if you want to try peaks yourself, please visit peaks.lectures.de. Thank you.
So, thank you very much for the presentation. Very nice presentation. I would like to welcome Fritz Lekšas, who we already saw in the video, and he is here with us to answer your questions. I see many applause to your great work, and also many wonder in a positive way about how you managed to put so much work and so much different contributions into one single paper. Really, congratulations on that. And we have two questions from Shivan Agrawal, and he also congratulates you very much on your contribution. And he has two questions. One is that it was mentioned that the convolutional autoencoder abstracts the data and finds a low dimension representation from 120 dimensions down to 10 dimensions. And his questions is regarding the usage of bar charts to represent the abstracted data and to formulate visual queries. And he says that since there are 10 dimensions, the peaks in the bar chart would highly depend on how they were projected on the bar chart. The question is whether it wouldn't interfere with investigation of sequence data or finding similar patterns for the classifier.
I'm not really sure what the gist of the question is. So maybe to clarify, the data that we feed into the convolutional autoencoder are not the 2D bar charts. So we feed in the one-dimensional data, which is normalized to between 0 and 1. So I'm not sure how it would interfere. If this is regarding the search throughout the entire data set, then what we basically apply is a sliding window approach to find, patterns that would otherwise be cut into two if you chop the long time series data set into discrete windows. I hope that helps a little bit. Otherwise, I'm happy to chat also offline or in the Discord channel more.
Yeah, I would encourage that also for all audience. If you have questions that come up to your mind later on, I'm sure the authors are approachable also beyond the presentation today. I think his second question might be more easier to answer, and the question is, what does those peaks represent? What do they mean? Do they have any biological meaning, or what do they represent?
Yeah, that's a good question. So the two data types we looked at are called DNA sequencing and histone modification ChIP-seq. And basically, what they represent is certain features of the chromatin molecule, which basically is the DNA string. And to keep it short, they basically inform us about certain modifications that and accessibility of the DNA string, which is important for physical interactions to happen. And ultimately, what that means is like you can find, for example, regions that enhance a gene, which then lead to more increased like gene products, like proteins, like in higher transcription, basically, of genes.
Thank you. There is one more question from Vít Rusňák. He asks, also congratulates you on the great talk, and he asks whether you could please elaborate more on the data pre-processing performance and or limitations, especially the data sample size and the processing speed, and if it is possible to use the peaks for real-time data. So I think these are more or less three questions. Maybe we start with the data pre-processing performance and limitations with regard to sample size.
So the pre-processing is very simple on our end. So we already rely on pre-normalized data. So we're not inventing a new normalization technique that has been defined by a consortium called ENCODE. That's where we get the data from, the biology data. What we do is we remove extreme outliers. So we cap the data at the 99.9 percentile, and then we normalize it or we map it to O2, like a region O21. That's all we do. So that's extremely fast. Training, of course, takes a long time depending on how much data you have. Our models train 3 to 7 days. But that depends on the model and how much data you have for your specific data type. And for live data, I guess the biggest question is whether you can estimate what the minimum and maximum values are, because in order, at least for our model to work, the data needs to be in O21. And if you don't know what the ends are, I mean, that might be a little challenging. But then maybe one approach that could be done is like instance normalization. So as you see a chunk of new data, you just normalize that data in accordance to the last, let's say, 10 instances that you saw, like that. Yeah.
Great. So is there also a limitation on the number of data that you can process at the same time and to show, for example, the length of the time series?
So visually, there isn't really a limitation. So the system uses a library that we developed called HighGlass, and that is based on tiled data. So we're never loading the entire data set. We are always just loading a certain tile, like a certain region of the data at a pre-processed aggregation level. So in that regards, it doesn't matter. Of course, what matters is like the overall pre-processing time increases the bigger your data set is. And so roughly for like 1 million windows, it took on my laptop 25 to 30 minutes on average to pre-process. Of course, if that is outsourced to a server, like a cluster system, that could be faster. But so if the data set is much larger than that, of course, the pre-processing time goes up.
Now came a clarification of the first question, is that how high the high-dimensional data was converted to the sequence of the normalized 1D data. Can be cleared. We have 1 minute still left, so we can talk about it, and then you can use the chat to discuss further.
Yeah, so the data is already one-dimensional, so it's essentially just count data. So if you think of the genome as just a sequence, it's like time steps. And then for each time steps, what we essentially measure is just count values. And all we do is we use the pre-normalized count values. Then we aggregate these values at a specific level, which is meaningful to the given the biological features, so that the vector then becomes 120 per window. And then we send this vector into the convolutional order encoder. I hope that helps. Otherwise, I'm happy to discuss this in more detail on Discord.
So thank you very much for the presentation and for participating in the discussion. I think now it's time to move to the second paper, which received honorable mention. The paper is Phase Space Projection of Dynamical Systems by Nemanja Bartolovic, Markus Gross, Tobias Günther. And it's presented by Nemanja Bartolovic. Let's have a look at the video first, and we take the questions up.
And welcome to the presentation of our paper titled Phase Space Projection of Dynamical Systems. My name is Nemanja Bartolovic, and I'm a PhD student at ETH Zurich. Today, I'd like to talk about the visualization of motion. To illustrate the problem, let us start with the motion of a pendulum. The motion of a pendulum is determined by two numbers, the angle and the change of the angle. A simple ODE describes how these two numbers evolve. If we plot the two numbers in 2D over time, we see that the pendulum traces out a trajectory. This 2D space is called the phase space of the dynamical system, and it contains all possible trajectories a pendulum can take. As another example, consider the circular restricted three-body problem, where an object, such as an asteroid or a spacecraft, moves according to the acceleration field of two celestial bodies, such as Earth and Moon. When restricting the motion to a plane, the object has four state variables, two for position, x and y, and two for velocity, u and v. This means that the phase space is four-dimensional. How do we visualize its trajectories? Or more general, how do we visualize trajectories of any dynamical system with even more dimensions? To answer this question, we developed a dimensionality reduction technique aimed at trajectories in the phase space of dynamical systems. Before proceeding onto the method description, it is worth exploring some of the related work on the topic of multidimensional data visualization. There has been a plethora of dimensionality reduction techniques developed throughout the decades with different strengths and limitations. We would particularly like to mention TSNE and UMAP, which have seen widespread use in different types of datasets since their invention. However, when we apply UMAP, for instance, onto high-dimensional curve data, we could obtain the result as shown on the right. The problem is that there is no strict connectivity constraint embedded in the algorithm, as it was designed to tackle generic high-dimensional point datasets after all. Even though the input curve is completely connected, the projection appears disjointed in several locations, as visualized by the red arrows. This is one of the problems that we aim to rectify. Beside the dimensionality reduction methods, it is worth mentioning interesting work in high-dimensional flow visualization. Hoffman et al. Developed a 4D camera projection technique that enables exploration of 4D vector field topology. With our method, we do not have a restriction on the dimensionality of the input data. Now we will describe the details of our method. The goal that we stated to accomplish was to project high-dimensional curves from a phase space down to 3 dimensions, ready for visualization. These high-dimensional curves, illustrated as dark gray in the image, are represented as sets of sample points, where each point has an associated position and velocity. In order for the projection to remain continuous and smooth, we define the projection operator as a non-invertible differentiable map P. With this definition, the velocity of the output low-dimensional curve, shown in green, is transformed by the corresponding Jacobian. The question remains, how do we constrain this map? Ideally, we would like to constrain it in a way that preserves some of the geometric properties from the high-dimensional space, such as the curvature of trajectories or the tangent magnitude. Intuitively, the goal is to replicate the behavior of the high-dimensional flow such that the faster-moving regions in the original data are represented by similarly fast-moving projections in the low-dimensional space. In order to support multiple trajectories in a single dataset, we also constrain the projection map with distances to neighboring curves. By considering neighbors, the spatial organization of the projected curves is significantly improved. Optionally, we can specify critical point projections. Critical points are equilibrium points in the phase space that have zero velocity. This constraint helps to pin down the whole projection around a specific location in the low-dimensional space. In order to resolve all of the aforementioned constraints, we parameterize our differential map P as an n by m polynomial map. Thereby, each row of the map represents one output dimension and is computed by an independent polynomial of up to d degrees, where d is user-specified. Given this definition, the problem boils down to determining the unknown polynomial coefficients that comprise the map. An example of such a map is given here, where we wish to compute a three-dimensional output and expect four-dimensional curves as input, with the polynomial degree set to 2. To find these unknown polynomial coefficients, we set up an energy minimization problem where we convert all of the desired properties into constraints. These constraints include curvature, tangent magnitude, neighborhood distances, and optionally the critical point projections. In addition, all of these constraints can be weighed individually in order to achieve the desired projection. The different weights are particularly useful if the orders of magnitude of different constraints differ a lot. Finally, we use a nonlinear least square solver to optimize for the projection parameters. In the following slides, we will showcase some of our results. In order to do so, we have applied our method to several dynamical systems. One such system is a circular restricted three-body problem which can be described in a four-dimensional phase space. Next, we have a damped double pendulum system where the equations of motion are observed in angles and changes of these angles. This configuration also lives in a four-dimensional phase space, where the state consists of the two angles and their changes. Last but not the least, we will also present a few examples with simulations of inertial particles in fluid flows. In such a system, we observe particles of a certain mass and starting velocity as they get advected by the 2D flow. If this flow is also time-dependent, the state dimensionality is increased from 4 to 5 to account for the time variable. As a first motivating result, we show a projection of a single trajectory of the CRTBP dynamical system. The motion of the particle can be observed by the red highlight, and we can see that its movement is continuous and consistent both in the visualized subspaces of the phase space and the final 3D projection. There are no sudden jumps or discontinuities in motion, and the projection also exhibits symmetric patterns. Next, we compare our results to other dimensionality reduction techniques. With principal component analysis, the projection is largely dominated by the increased values of the velocity subspace, hence the disk-like appearance. Both TSNE and UMAP produce interesting visualizations, but sometimes have unexpected discontinuities along the curve. Our method is shown for comparison. One of the metrics that we use to assess the utility of our results is the stability with different integration durations. We run 3 simulations of different time durations and project them independently. As a result, we obtain very similar looking projections that differ only by the length of the input curve. Compared to our projection, other methods tend to produce very different results, even though the underlying phase space manifold remains the same. In addition, we can notice an emergent structure with the UMAP projection, but that unfortunately requires a lot of samples which may not always be feasible. Next, we show results for the double pendulum system. The initial configuration consists of 4 different trajectories, each starting from the same position, but due to varying starting velocities, end up in different final rest states. When using our method to adjust the geometric constraints to project these trajectories, we obtain the result in the middle. We can notice that the resulting projections are fairly interwoven and difficult to discern. After enabling neighboring constraints, the new projection map spaces out the curves according to the corresponding distances, and the resulting projections become easier to see. In the following configuration, we once again have 4 trajectories of the double pendulum system, but set up in such a way that 2 of them end up in one critical point and the other 2 in another. Our map preserves this assumption from the high-dimensional space by projecting them around their final critical points. In contrast, TSNE and UMAP attempt to separate all the trajectories as individual, distant entities and inadvertently break their connection to the associated critical points. Another interesting result is the explicit representation of our projection map. Given this formulation, we can apply an optimized map to new similar data compared to the dataset that we have optimized the map with. As an example, we show inertial particle motion in a forced Duffing equation phase space. We jointly optimize 3 different trajectories, yellow, purple, and orange, and visualize corresponding critical points as spheres. Next, we repeat the optimization process, but include only the yellow and purple trajectories. Finally, by just using the projection map from the middle illustration, we explicitly project the orange trajectory without optimization. As a result, the orange projection appears in a similar way as if it was jointly optimized with the other trajectories. This is possible due to the smooth and continuous definition of the projection map. The results that we have shown so far have been derived from 4-dimensional curves. The first higher dimensional scenario shown here is given by the inertial particles in a time-dependent flow, where the input curves are specified in a 5-dimensional space. The 6-dimensional example is obtained by projecting a curve from the CRT-BP system, but configured in a way that allows for motion in the z-axis, effectively increasing the subspaces of position and velocity to 3 dimensions each. Another important aspect of the optimization are the weights. We have mentioned that they are useful in order to balance different constraints accordingly. For the following images, we assume a single trajectory simulated in the 3-body system. First, we show a projection that is obtained when we project this trajectory using only the curvature cost. The colors on the 3D visualization match up well in the upper part where input and output curvature is visualized, but differ for tangent magnitude in several places. Next, we have the same setup, but optimized only for the tangent magnitudes. In this case, there is a large difference in the curvature of the input and output curves. On the other hand, the tangent magnitude matches perfectly. Finally, we enable both of these constraints and perform the optimization. We can see that both costs are now matched up well. In addition, in a variety of cases, this cost configuration tends to give the best visual clarity of the projection. In the following video, we show how the optimization proceeds in real time for a single trajectory that consists of 5,000 points. Since the optimization is iterative, its intermediate steps can be visualized and can be interrupted at any time. Finally, we would like to list some of the limitations that we have identified with our method. The objective function is non-strictly convex, which may lead to different local minima. While computational cost was acceptable for the majority of datasets we have used, the scalability and performance issues arise with higher input dimensions and larger datasets. In addition, the projection map is not invertible, which could lead to different points being mapped to the same location in the projection. This problem is generally mitigated with the usage of neighborhood constraints. In summary, we formalize the projection of a high-dimensional vector field and describe its local and integrated flow properties. We formulate the projection as a tensor product and optimize the projection for varying polynomial degrees. In the future, we would like to explore different optimization schemes that could be used to optimize the projection map, as well as work with higher dimensional data and improve overall scalability and performance. Thank you for your attention.
So, welcome back. We now have finalized the second talk, and we have a couple of questions. Thank you very much for the presentation, and also welcome our presenter, Nemanja Bartolovic. And I would like to pose the first question from Ingrid Hotz. Do you have any practical application in mind, or are you already collaborating with somebody on this issue? Applying?
Yes, so the first part, I suppose the main application in the beginning was to visualize the geometry of the phase space, especially of the high-dimensional phase spaces, and to see how different curves and trajectories relate to the critical points that can be found in these phase spaces. This could help anywhere where, for example, you need to summarize the contents of a phase space, which is super high-dimensional. And idea is, of course, to also use this with even higher dimensions. We just presented some of the works which where we could easily obtain data which is high-dimensional, which means 4D, 5D, 6D. It's a bit easier to simulate that and work with that than to directly apply it on some even higher dimensions. As for if we're collaborating with someone, well, we did have an idea to use it on some extremely high-dimensional data sets, but that's something that's up for future work and investigation.
Thank you.
So yeah,
there's also a follow-up question on follow-up on the application side, and the question is whether you also investigated how the projections of attracting and repelling manifolds look like. Can they be identified in the projection?
So we could, of course, project some of the critical points. And it's even better to start off with some of the known critical points, like, for example, positions where velocity is 0, where some of the other points will either leave from or attract to or be repelled. This can be specified directly as a constraint, or it can be also visualized in the output, assuming that some of the locations do actually have a 0 velocity. You could assume that. But of course, this could also be a false positive in the projection because of the way that it's not invertible. So you could have some points also mapping to this particular position. But in practice, we didn't have these problems. So in a way, we can visualize how the dynamical system would behave roughly around a certain critical point. I hope that answers your question. Of course, given that it's a dimensionality reduction technique, you cannot preserve all of the information that comes from the high-dimensional space.
Is there a limitation to the number of critical points, or?
Well, in practice, you can specify any amount you like. For a double pendulum system, for example, we typically experimented with like 4 or 8 or 16, depends on the problem and the setup that we wanted to show. So I wouldn't say there's a strict limitation, except for perhaps if you stretch the space out too much to include too many critical points, if they're repeating all over the phase space, perhaps the optimization, the results will not look, well, it depends if the degrees of freedom of your projection map can cover it so well in such a large space.
Are there any more questions? I don't see any more questions, so I would like to also ask one question about the parameters that you use. There are several parameters that need to be set. Is there any guidance on setting those parameters, or do you have any rules of thumb that you can use?
Well, ideally, if you want to strictly preserve the locations of the suggested locations of the critical point locations, because they're unknown, you cannot really determine them. We suggest using a high lambda, for example, for that, so that the projections are that constraint is really embedded into the map. On the other hand, for other constraints such as the curvature and tangent magnitudes, I would suggest that perhaps they be balanced out such that the orders of magnitude remain the same during optimization. So, for example, if curvature is in range of 0.5 to 1 and tangent magnitude is within a range of 10 to 50, you would perhaps multiply curvature by some value of 20 or something to make sure that the weights are balanced out and the constraints are both optimized jointly together. On the other hand, for the projection itself, I would always suggest, even though, for example, some other papers and methods suggest that rerunning the simulation, especially because we have this initial guess step in the beginning where we try to guess the map and then work from there, to rerun the simulation multiple times to get the minima that we want. I would suggest that the data set that we're working with should also be run in a subsample manner, where we, for example, remove every second point and then project it again. If we get the same projection or a similar projection, we are sort of very close to approximating the phase space manifold, hopefully, as long as the projection remains stable and similar in a way. That's the thing that we also shown with different integration results, and we also in the paper show the similarities across different time steps. So we could also get a similar projection then. This will be the main guideline. So to use the lambdas to equalize the constraints and to check the validity or sort of the correctness of the projection by evaluating it with different integration durations or different time steps.
So, thank you very much. The time slot has been use for very interesting questions and answers, and the video presentation of the great paper. Congratulations on the honorable mention, and thank you for joining the discussion session. And now we move to the next paper, which is called Infomages, Embedding Data into Thematic Images, that also has received an honorable mention, has been written by Darius Coelho and Klaus Müller. And the presenter, Darius Coelho, is with us today and takes your questions during the video.
Hello everyone, I'm Darius Coelho and I will be presenting my work, Infomages, which is about embedding data into thematic images. This work was supervised by my advisor, Klaus Müller. So let me start off by telling you what infomages are. Infomages are a type of infographic that consists of a data chart that is embedded into a thematic image. This example was created by Peter Ontoft and shows data about the perception of wearing a burqa in the workplace. So why study infomages? First, they have been gaining popularity and often appear in newspapers or blog posts. Second, their properties have been shown to be beneficial by previous studies. They contain human recognizable objects and visual embellishments, which have been shown to promote engagement and have also been linked to improve memorability. However, these graphics are difficult to design and have been mostly produced by professional designers. Our work aims to make the design of such infomages more accessible to novices by creating a novel design tool. But before creating our design tool, we first conducted a survey of existing infomages. We wanted to first understand how professionals have gone about creating these graphics and then apply these principles to our tool. So we first collected a set of images for our survey. We used the term photographic infographic to retrieve infomage-like graphics using Google Images and Pinterest. We also used the related images feature of these websites to recursively collect more images related to the initial results. We collected an initial set of 1,638 images. We then filtered the images that did not fit the definition of an infomage, leaving us with 224 infomage-like graphics. But it should be noted that we relaxed the condition for the image to be thematic so that we would have a larger set of images to study. We then used Google's reverse lookup of images to see if we could identify the creators of these images. We found that a large chunk of the graphics, 188 to be exact, were created by professional designers or design firms. We then coded each image based on the type of chart they used, the embedding methods employed, and if the image was thematic or contextual to the data. So let's look at the chart types first. We categorized the graphics we collected into 7 categories based on their chart type. The first and most popular is a bar chart, which were present in about 41% of the graphics. Here an image object is used to represent a bar in a bar chart. For example, a man here represents the bars in a bar chart. The second most popular was a pie chart, which was present across 21.4% of the graphics. Here a pie chart is embedded into an image object. In this case, a pie chart was embedded into this man's kippa. The next chart type is a single divided object, covering 12.5% of the graphics. As the name suggests, it is an image object that has been divided into multiple regions, where the region's length or area represents a data value. In this case, a cake's layers represent the different data values. Next, we have the multiple resized object type, which was present in 11.2% of the graphics. Here, multiple objects in the image are resized to represent data values. In this case, multiple balloons of different sizes represent data values. Next, 9.4% of the graphics consisted of line charts. And here an image object, like the green straw or edge of the cheese, represents data values over time. We also had a few scatter plots, 2.2% of the graphics to be exact, with various image objects representing points, axes, and areas. Finally, all other visualizations that occurred only once, such as sunburst charts or contour maps, were put into the others category, which covered 2.2% of the graphics. Next, we categorize the graphics into 4 categories based on the method used to embed the chart into the image. The first and most widely used technique is the replicate and transform technique, which was present in about 49.6% of the graphics. In this method, an image object is replicated and then transformed by resizing or repositioning it. In this image, we consider the balloons to have been replicated, resized to represent data values, and repositioned in descending order of the data values. Next, we have the fill method, which was employed in 29.5% of our set of graphics. Here, objects are filled to represent data values. In this case, the men in the image were filled with a texture to different levels to represent data values. Next, we have the overlay technique, where the chart is overlaid on an image, such that the edges or objects in the background have a shape that is similar to the chart. This method is employed in 15.6% of our graphics. Here, the curve created by the mathematical function matches the curve produced by the plants in the image. The final technique we observed was a cutout technique employed in 7.1% of the graphics. This technique is straightforward. Here, the chart is used to cut out part of an image. In this example, a line or area chart was used to cut off the lower part of an image. Finally, we examined if the graphics we collected contain thematic backgrounds. 52.6% of the graphics use thematic backgrounds. For example, this graphic is thematic since it shows the data about the perception of religious symbols at the workplace. On the other hand, 47.4% of the graphics did not use thematic backgrounds. For example, here a piece of cake is used to show data about the reasons for not casting a vote in an election. Based on what we learned from our survey, we created an Infomage design tool that allows users to create such graphics with relative ease. So let me give you an overview of our tool's workflow. The user starts off by loading in a data file. Our tool first retrieves images related to the data. We do this by extracting the attribute labels as well as the name of the dataset, and use this information to retrieve images from a search engine such as Google Images. We also allow the user to import an external image. Once the images have been retrieved or the user imports an external image, the user moves on to the data embedding process. The user can select from two of the surveyed embedding methods, fill and overlay. Each method supports multiple chart types. The embedding methods can at times cause some chart distortion. Thus, the next step of our tool is to estimate this distortion. Based on previous studies, we develop methods to compute the amount of distortion introduced to a graphic. We also develop methods to optimize the distortion. Once the user is satisfied that the distortion is acceptable, he or she moves on to the post-processing step. This involves chart styling, such as changing the colors or adding glows to chart elements, or filtering the background image, as well as styling the fonts, thus creating the final Infomage. Due to the time limit, I will only discuss the details of our data embedding and distortion estimation method. Let's start with the data embedding techniques. We focus on the fill and overlay technique in this work. We exclude the replicate and transform technique as it has been well studied and implemented in tools such as DDG, Data Inc., and Infonize. We also exclude the cutout technique as it is straightforward and not very popular among designers. So let's start with the fill method. Given a data set and an image, in this case, data about lipstick brands, we can embed the chart into the woman's lips to create an Infomage. To accomplish this, the user must first roughly select the object region, in this case her lips. We use this marking to guide the GrabCAD segmentation algorithm to segment out the lips and create a mask. This mask is then used to fill the pie chart into the lips and create an Infomage. Our fill technique can be used to support pie charts, a single divided object, or a bar chart. In pie charts, the area can be divided based on the angle, area, or arc length of each segment. The single divided object and bar chart can be filled based on length or areas of the image objects. The other embedding method we support is the overlay method. Here, we have a data set showing the number of UFO sightings reported over the years, and an image of a flying saucer attacking Earth. To create an Infomage, we must overlay the chart on an appropriate image region. We do this by computing the regression line of the data to represent an overall trend and detecting the half lines in an image. We then find a matching half line that has a slope that is closest to that of the regression line. We then use this half line to determine the position of our chart by overlapping the centers of the half line and the regression line to create our Infomage. With the overlay method, we support line, bar, and pie charts. However, for pie charts, we use half circles instead of half lines. The embedding methods, especially the fill method, add some distortion to the chart. In case of the fill method, the areas, angles, or arc lengths of the segments may not match the proportions of the original data. And in case of the overlay charts, the line or bar chart can get distorted by choosing an inappropriate aspect ratio or changing the range of the y-axis to change the perception of the trend. To report such distortions, we compute the difference between the actual data and the plotted values. In fill charts, we compute the plotted values by measuring the area, angles, and length of segments of the Infomage. We then report the difference between these values and the actual data values as an average % error across all segments. This error informs the user that on average, their Infomage may cause viewers to over or underestimate the data value of each segment by the reported percentage. In the case of overlay charts, we detect if the intersection of the x and y axes is 0, and if the average slope between the plotted data points is 45 degrees as stated by the 45-degree banking rule. We report any differences as a percentage error. In addition to computing the distortion, we also provide methods to optimize the distortion. For fill-style charts, we optimize the distortion using the simulated annealing method. This method basically varies the distortion until an optimal level is achieved. Here, we add or subtract random small noise from the data values while ensuring their sum is equal to that of the original values. We then compute the chart distortion, that is the average error based on the area, angle, and arc length. If this error is lower than the previous error, we accept the distortion. We keep doing this until the change in error is extremely small for repeated iterations or if a decay function converges. It should be noted that we also accept higher error values at random. This is done to avoid hitting local minimas. To optimize the distortion in overlay charts caused due to the aspect ratio, we compute the optimal aspect ratio by banking to 45 degrees using the average absolute slope banking method developed by Cleveland. These methods are all packaged into a Windows-based interface shown here. I won't be able to explain this right now due to time limits, but you can check it out in our video. The final part of this work is a user study that tested our design tool. For the study, we recruited 5 participants, 4 males and 1 female who were all grad students. They were first given a tutorial and allowed to practice interacting with our tool. On average, this took them 21 minutes. Next, they had to perform 2 main tasks for the study. The first was a replication task, where they had to replicate in 1 overlay chart and 2 fill charts, a single object and a multiple object fill chart. The second task was a creation task. They were given multiple datasets and they could select any dataset they liked and create an Infomage of their choice. We studied 3 main aspects. The first is the tool's functionality. The participants took an average of 4 minutes and 49 seconds to replicate a single Infomage and 13 minutes and 11 seconds to create one from scratch. It should be noted that they spent more time with the overlay charts, as those charts had more elements to play with around during the post-processing, such as line or bar glows, access as formatting, and more. Next, we asked participants to rate our tool's usefulness with a 5-point Likert scale. They rated the tool as easy to use with an average rating of 4.3. They also agreed that it was easy to learn with a rating of 4.6, while they gave it a lower score when asked if it performed as expected. They state that at times the segmentation was not accurate, although it was easy to perform. They also stated that the placement of line charts was not perfect and appeared at locations they did not expect. Second, we asked the participants what they thought of the distortion estimation. They all stated that they understood what the distortion values indicated. However, they also stated that they did not know what the level of distortion would be acceptable. Finally, the participants liked our image suggestion feature, but stated that they could find better images on their own, and they did so during the study. To summarize, we conducted a study of existing Infomages, and based on what we learned in the study, we created an Infomage design tool that helps users easily create Infomages, as well as estimate distortion in these images. We also conducted a usability study that showed in general users found the tool easy to use. However, this is a first step, and there are several aspects that can be improved in the future. The first is to define a good level of distortion. This is an extremely difficult task and requires a large-scale user study. The next is to develop a better image retrieval, as that is something the users complained about. They also stated that our segmentation and alignment methods could be more accurate, so that is something else that can be improved in the future. And finally, we hope to extend our embedding methods to a fully automatic approach. Thank you.
So, thank you very much for the presentation. Congratulations on the Honorable Mention Award. I think the impressive images already show how great this work is, how it shows the power of combining infographics into images in several different ways and automatic way of creating images directly in images. And yeah, I don't see currently any questions from the audience. Therefore, I would like to start with my question: is the coloring scheme that you use. Can you maybe tell us something more about how do you combine the colors from the original image when choosing the colors for the embeddings and fillings?
We don't really do any automatic color suggestions or anything. We do provide some of the color palettes from the suggested color palettes, but when we merge them with the image, we do it in the LAB color space, where we keep the L channel constant and change to A and B so that we keep the textures of the image.
Do you provide any recommendation for the users where to place the embedded infographics? So, for example, not to overlay very salient parts of the original image, or is there a free choice where to use the overlay?
It's a free choice. However, for the overlay chart, we try to center it on the half line or the half circle center that we detect.
You mentioned that you did a big survey of the methods and of the images. Maybe you tell us something more about the methodology, how you searched for those images, because it's not very easy to find it on Google, as you mentioned. Was there any kind of tricks that you need to use?
Yeah, so actually, it was very difficult to find them using like terms like infographic or infographic with pictures or something. We tried a lot of these terms. We got one or two of these images, but not a lot. But upon clicking one of them, I came across this blog that says photographic infographic as a title. And we used that term, and it actually captured a lot of these kind of infomages. And still not as much as we expected, but once you click on any of these images, you get like a set of related images suggested by Google or Pinterest. And we then retrieved those images also. And we did it up to like two levels deep in recursively.
There is a comment from Jason Dykes on YouTube of whether anybody knows the level of the distortion that is acceptable. Have you considered making a study about setting the parameters, a user study?
Yeah, we do have a preliminary study in our supplementary material. And for the fill style charts, people start to get like go wrong with them when there's like, especially the pie charts, when there's about 10% or 15% error. But the overlay style charts, it's about 20% error. They start to go wrong. But I think in my previous presentation, Jason Dykes also said that maybe people need to just live with the errors. And to comment on that also, that I think the Beyond Memorability paper by Michelle Balkin also suggests that people more or less look at the text in the images. So probably the text offsets this a bit. Yeah.
Okay. Yeah, definitely. I agree with Jason that there is no one single level. Yeah. We can get some orientation or guidance on the default values that one could use. I do not see any other comments. So I would like to thank you very much for the nice paper and submitting to Eurovis. Congratulations on your award. Thank you for joining the discussion. And I would like to... Jason says that if you ever find it, then you should let him know.
Yeah, sure.
And, okay. And with that, I would like to thank you very much for your great work. We hope to hear from you soon on the distortion levels.
I'm not sure if I will find it.
I'd like to conclude this third talk and move to the next one, which is Localis, locally adapted line segmentation for GPU-based geographic vector data visualization. I think this talk makes us all that sit at home in a home office and currently dream of going for a hike and cycling again. And please enjoy the talk.
Welcome to this presentation. I'm Ali Reza Amirakdam from the Visualization and Multimedia Lab of University of Zurich. In this video, I will present our locally adaptive line simplification algorithm called Localise, which is mainly designed for visualizing geographic vector line data, but its application is not limited to this field. Vector line data is an abundant type of data in geographic datasets. The level of detail is usually managed by creating different versions of the dataset generalized at different levels. The shortcoming of this approach is that different levels of detail cannot be used side by side in one scene. In a 3D visualization, this shortcoming becomes critical because in many viewing angles, different levels of detail are required for different parts of the scene, depending on the distance to the camera. Otherwise, either the close parts will be too low in detail or the far parts will be too cluttered. Additionally, a large unnecessary data should be handled. To tackle this challenge, we have developed Localise. Localise simplifies lines non-uniformly, is based on a pixel-precise visualization technique for large vector line datasets, takes advantage of the GPU parallel computing power to run in real time, prevents unwanted intersections, and dynamically changes the thickness of the lines to reduce the clutter. I will explain each of these features starting with non-uniform line simplification. Our algorithm is based on Douglas-Poiker line simplification. For each line, we start with the most simplified version of the line. Then we add the point with the largest distance to the baseline. This distance is denoted as error. This point divides the line into two parts. For each part, we apply the same procedure, and in the end, we have a binary tree with nodes that represent points and their corresponding errors. After saturating the errors hierarchically, such that no node has a lower error than any of its descendants, we can simplify the line by pruning this tree while traversing it based on any given error threshold. Like this example, the error threshold can be a function of distance to the camera. Next, I will explain our pixel-precise 3D visualization of large line datasets. Recently, differed vector rendering is introduced for visualizing large number of lines in 3D, which takes advantage of the power of GPU. Localise uses the same concept. The color of each pixel is determined independently by comparing the distance of the pixel to the lines and the thickness of the lines. To limit the number of comparisons, an optimized search hierarchy is used composed of one grid and one quad tree in each cell of the grid. As a result, Localise provides a pixel-precise rendering of a large number of lines at any zoom level without using proxy data structures. Now I explain how we parallelized our algorithm to run efficiently on the GPU. Direct access to the vector data on GPU is a benefit. However, it is not possible to traverse trees redundantly for each pixel in real time. In order to make simplification possible in real time, we first create a set of all possible line segments that can emerge during the refinement process. The visibility of each of these line segments depends on 2 points. For example, this purple line segment will first appear when this green point is included. We call it generator, and will disappear as soon as this red point is included. We call it splitter. Storing all possible line segments with the generators and splitters as their attributes allows us to determine the visibility of line segments individually, which fits the parallel processing nature of GPUs. In order to have a valid line, no point should be included in the line when even one of its ancestors is excluded. In this example, the red point should not be included when the green point is excluded, or the green point must be included when the red point is included. This can happen when the error threshold is a function of distance to the camera and the ancestor is located farther from the camera. To solve this, we conservatively assume a lower distance to camera when validating the green point, such that none of the points in the subtree can be possibly closer to the camera. The amount of this decrease is the maximum of distances between the green point and the points of the subtree and is denoted as Dmax. We calculate Dmax beforehand and store it with each point. For the same reason mentioned earlier, we also saturate Dmax. Lines can now be simplified non-uniformly based on an error function on GPU. In this example, we are using a lens that has a low error threshold inside and a large error threshold outside, thus high level of details inside and low level of details outside. The details are being added and removed to the line as the lens approaches and hovers over the line. In this example, the underlying set of all possible lines are also shown for demonstration purpose. Another challenge is to prevent intersections between lines when they are simplified. To solve this, we find all possible intersections. An intersection can happen when a point, such as B, is located in the triangle that excluding another point, such as A, creates. In this situation, excluding A before B results in an intersection. To prevent such intersections, we find all such dependencies and involve them in the saturation process of error and Dmax. As a result, no dependent point will be excluded before its dependees and no unwanted intersections will appear. These two examples show the unwanted intersections that can happen on the left and how Localis prevents them on the right. The last feature I explain is dynamic line thickness. Localis can dynamically change the thickness of the lines using a given function. This can be useful in wider viewing angles to keep the important types of lines visible while the others fade into the background. In summary, we get the lines as an input, create binary trees using the Douglas-Poiker algorithm, calculate error and Dmax values, find the intersection dependencies between lines, saturate error and Dmax values within trees and between intersection dependencies, and finally create a list of attributed points. At the same time, we create all possible line segments, find their generators and splitters, and create a list of attributed line segments. Then this data is loaded to GPU and rendered in the deferred vector map part of Localis. During the rendering, simplification happens on the GPU and this data is not required to be updated. Now let's watch Localis in action. In this test, we are visualizing the whole street data of Switzerland with 6.9 million line segments over a static train with all features of localist active. The performance ranges from 6 to 75 frames per second in this setup, which is indicated at the bottom at several points as we go on. Localist increases the thickness of the important types of lines when zoomed out, so only the important lines are visible. As we zoom in, other lines become visible gradually until they reach their actual thickness. By default, the error threshold is a function of the distance to the camera. Instead of bounding the error threshold to the distance from the camera, we can adjust the error metric manually, which causes all the lines to be simplified uniformly at the same time. We can also use a refinement lens. The error threshold inside the lens is low, which causes all the lines inside to be at their highest level of detail. The error threshold outside of the lens is high, so the lines outside are simplified as much as possible. We can see that the details of the lines adapt to the movement of the lens immediately. Since we use the deferred vector map rendering technique, the lines are always pixel precise no matter how much zoom we apply. If we visualize the underlying quad trees, we can see the size of their nodes and how the line segments are distributed. The brighter nodes contain more line segments, and for the pixels inside these nodes, the GPU shaders have to do more distance to line comparisons to determine the color. This is the main reason why the performance is different at different zoom levels. We successfully implemented a real-time non-uniform simplification for vector lines in 3D by performing the operations directly on the attributed vector lines without using proxy data structures. The take-home message is that we can perform computationally intensive operations on vector data at render time on GPUs, which creates opportunities to increase the fidelity, flexibility, and responsiveness of the visualizations. Thank you very much for your attention.
So, I would like to welcome our presenter, Alireza Amiraktam. Congratulations on the award. And also, not only on the great paper, but also on the great presentation. We have seen many very positive comments in the YouTube. And people like your work very much. Maybe they want to really go hiking or cycling finally outside in the countryside.
Yeah, hopefully. So, thank you very much.
We have one question from Sebastian Weiss. He also said that the work is very, very nice and would like to know how long does it take to pre-process the data. Could you maybe elaborate a bit about the pre-processing?
So the pre-process depends on the CPU, and it's done once before we can run the program. And we tested on two different machines. On one of them, it takes around 7 minutes to process our largest data set. On the other one, it takes around 12 minutes to complete the pre-process. So this is the range.
And there is also a question by Bob Larmy. How much additional memory does the binary tree require? So how many memory resources do you need?
In comparison to like a normal rendering, or so I have some numbers, and they're also they are in the paper. So for if we have all features on for our largest data set, we need something around 2.9 gigabyte of memory to put everything on the GPU, and we don't need to update anything else and have this visualization as we see.
in the presentation. This number for a very simple rendering of the lines would be something around 380 megabytes. So now we can compare it, these two numbers.
So maybe you can tell us a bit more about on which data sets you evaluated your.
So we used two data sets. We tested everything on two data sets. Both contains the whole street data set of Switzerland. One is from OpenStreetMap, another is from SwissTopo. One has 6.9 million line segments. The other one from SwissTopo has 11.1 million line segments. And for the 6.9 million line segments, we need 1.8 gigabyte of memory in the end, with everything included. And for the 11.1 million line segment data set, we need 2.9 gigabyte of memory in the end, everything included. And if we exclude dynamic line thickness, so only have the simplification part, these numbers are reduced a lot, which goes for the first data set, it goes to 1.3 gigabyte, and for the second data set, it goes to 1 gigabyte of memory RAM.
So there is also a question from Jason Dykes. Hooking that map lines on an eye tracker might be interesting. He doesn't suppose. Yeah, the question is whether you have tried to do that.
Yeah, that's a very nice question, because we didn't try it yet, but it's an ongoing project of ours. So in the next step, we are going to use this algorithm, this simplification in a foveated environment, where we can detect the gaze and simplify the lines in the peripheral region of the vision and keep the details in the fovea. Yeah, that's something we want to try.
Do you have any limitations on the number of bands the lines can have, like the fine resolution that you can use, or?
No, any type of lines can be used as long as there is no self-intersection. So self-intersection might be a problem, because we detect also the intersections and avoid them, like unwanted intersections. And if the lines have already intersections, that might conflict with our intersection prevention part of the algorithm. Yeah, but other than that, I don't think so. We can use any type of lines. Something else that we must have in the data set is, right now we simplify the lines between the joints. So if there's a crossing or a joint in between, we split the line, and we made sure in the data set that we don't have such intersections in the middle of the lines. That's another restriction. Other than these two, I don't think there's anything else.
Yeah, your work is getting a lot of positive comments and also questions, and one of them is by Bob Laramie. Where did you get the idea? What inspired your work?
So the inspiration came from the previous work, which was rendering vector lines in a 3D environment. And there we could see, okay, on the far parts of the scene where the resolution is lower, the lines are cluttered, and even there is a very advanced rendering algorithm there, but still we cannot detect the lines, and like it's not readable. So from there, it inspired us that, okay, we need some kind of simplification here, so that we can load the data set, a vector data set, that match the different resolutions of the parts of the screen. So the parts that we don't need a high detail, we can simplify the lines and keep the details in the parts that we need them, and we can show them.
Have you also considered any kind of degree of interest function? Like, for example, the hikers might be more interested in the mountainous roads rather than the exact streets in the valley.
So right now we have importance categories, which is set to the like highways have the highest importance, then major roads, then secondary roads. That's what we use. If we can detect these lines, like the interesting lines to bikers or any other interesting lines, then we can assign importance to them. So detection, so we use this highway and these categories because they already existed in our data set. But if we can detect the interesting lines, then yeah, we can assign importance to them. And for example, in zoom out views, we can keep those lines instead of the highways. So if we, in this presentation, if we zoom out, only the highways are visible. But in that case, we can keep the interesting lines visible in zoom out views.
So we are getting more questions and we have some more time. So there is a question, how does your work relate to view-dependent progressive meshes?
So the concept can be the same somehow, but there's a difference that here we load everything in the memory. So in our approach, we load everything, and then on the fly, per pixel, we decide which one is visible and which one is not. But in a progressive mesh, I guess, the detail that is needed are loaded gradually as the viewing angle changes or zooming out, zooming in. So I see that main difference there.
Okay. I see only one more comment or general question that can wrap up your talk, which is whether we will be able to use it somewhat soon in one of the mapping applications. Whether you consider publishing this work, make it usable also in the
publishing. Yeah, I hope so. So I think that's the goal of every researcher, to see the result of their research, their work being used somewhere in a real application, in a real world, and help people. So I hope so, yeah. And from the beginning, we try to use as minimum as possible the advanced features of the graphics card, so that we have the possibility to run this algorithm in a variety of platforms. So from the beginning, we had this in mind, and I'm very hopeful that we can see such an algorithm in existing map applications later. Even it can be run, I guess, in a web application because of these features that we used in this algorithm. Yeah, I'm very hopeful.
So thank you very much. I would like to thank all the presenters and all the co-authors of these 4 papers. It's a really wonderful work, and I would like to thank also the audience for watching and for asking questions. This video will be also available afterwards, so if you missed the session or part of the session, would you like to revise something, this will be still online for after the conference. And if you have more questions, please reach out to the authors. And with that, I would like to thank you very much for your attention. Bye.